All right, are you guys ready? Are you guys ready? No? Yes, we got thumbs up. All right, so let's go. Class. Okay, good. Thank you. All right, so we're starting this problem over again. We did a little bit yesterday, but we spent a lot of time on homework. I think that was actually more productive. And we did not finish this problem, but I don't want to pick up a problem halfway through. So I'm just going to state it again, okay, and go from there. So these problems right here I said was key is going to be able to draw it and understand what it is that this is actually saying. A rectangular swimming pool, 10 meters long, 5 meters wide, has a depth of 3 meters at one end, 1 meter at the other end. If the water is pumped into the pool at a rate of 300 liters per minute, at what rate is the water level rising when it is 1.5 meters deep in the end? Okay. I'm going to start by just drawing what we have. So, from a top view, it is 10 by 5, right? So, if you're in an airplane looking down on this pool, it's 10 by 5, right? Okay, good. Now, this next piece is going to be the part that is going to probably get us the most in trouble. Side view. This is 1 meter on this side. This is 3 meters on this side. Now, the volume of a pool, which is if it was a perfect rectangular pool and all of it is uniform depth, I would do the volume by saying length times width times height. That would be the regular cube. Okay? A regular cube look like this. Height going up and down, length right here, and width going back there. So length times width times height. Yes? That would be a regular cube. But the problem is the height depends on the level of the water. So if it is more than so this right here coming all the way across, if it's more than 2, the height of the water is going to increase at a constant rate because that is a regular. But below 2, right here, my length is going to be changing. My length is changing according to my height. So this over here is my length, and this is my width. Now, I'm going to go with some simpler type of geometry terms. So in geometry, I'm going to have a square. Okay? That's a square, right? Yes? Hopefully? Okay. So to find the area there is just going to be, okay, that's a length times width. Now the next thing we're going to do is we're going to add depth. We're going to turn this square into volume by giving it depth. So now it is going to be a tall that's going to be my height. So the volume is length times width times height. So technically, my volume is the area times the height. Yes? So on all these shapes that you're actually going to do, it's technically the area times whatever height or whatever thickness you're going to give that. So we're going to use that information to actually be helpful here. So let's go through, and I know that since I gave each one of those values, I wanted to know that in my pool, my width was 5, my length was 10, my height is equal to my, what was it, 1.5? They gave us a height, right? Christian, it was 1.5? Okay.
Yes.
Alrighty. So that was 1.5. And what else do we have? We had the volume, right? The volume going in. So my volume going in, so that was a dV dt 300 liters
Yep.
per minute? Okay. That's a lot of water. It really is. What else did they give us? I can go back. What is the rate of the water level rising? Okay, so that means I'm looking for dH dt. Now, when we were working on this yesterday, we were talking about it, and that's kind of where I left off. I'm going to focus on the cross section of the pool. My height and my length. So the height right here was 1.5, and it is whatever my length was supposed to be. You guys agree? Yeah? Maybe, hopefully. Yes? Okay. So this is what I had to focus on, because right here, at this part, this is going to give me a similar triangle to what I was looking for. So the whole thing, I know the whole length of the pool right here, this is 10, right? What is this side over here going to be when this triangle has the length of 10? Not 3, because remember, 3 is the full depth of the pool. So what would it? Let's go back and look. It would be just 2, right? Because this is the part that I'm focusing on here. So we're only focusing on this. So the height here is 2 when the length is 10. And as soon as we get to the point, I'm going to show you why this is going to be important. So I have that ratio set up, and I I do that for a reason, because when I go and find my volume, when I go find the volume, my volume would be equal to the area times the whatever this one's going to be. So in this case that I have right here, my 5, which is my W, here, let me back that up, times whatever the height is, so it's the triangle, so that's 1/2 the height times the length. So this is the triangle, and this is right here. This is going to be the thickness of that triangle. So this whole thing is going to go back out this way. Like that. Something like that, right there. Maybe? Possibly. Christian, no. You don't know what's going on? Where'd I lose you?
Why is it 2?
Why is it 2? Okay. What's the whole length from here to here?
3.
3. What's the length from here to here?
Oh my god, okay.
That's it. No, something simple like that, right? Just don't shake your head and be like, oh, crap. That, yeah. All right, so there we go. So we're going to set up a proportion, and I'm going to show you in a moment why it's going to be super important. So I know that as my height changes, is my length going to change also? So technically, as these two things change, I'm going to get a dH dt, and I'm going to get a dL dt. As those go, but do I have anything having to do with dL dt here? No. I don't. So that's the reason why I need to use the ratio of this. And so I'm going to use this, and you'll see why in a second. So I'm going to say that my height, the ratio of my height to my length, is going to be equal to 2 over 10. Hey there. I have second hour. Okay. So I'm setting up a ratio 2 over 10. So now watch this. By doing that, I'm going to get 2L equals 10H. Divide both sides by 2. So I could replace L with 5H. Huh? Can't I flip the L and H? So 2 is the height, right? Length is 10. So as we do cross products here for the ratio, so that's where I get that from. Now by removing, I'm going to substitute, and this is the reason why this is completely different from what we were doing. That's the reason why I wanted this to be, its own lesson. I'm going to replace L with 5H. So in my volume problem, one half height times length times width. Right? So my length, I'm gonna replace my length. So volume is equal to 1/2 H times 5H times W. In this case, is W changing at all? That's that 5, that's the width of the pool, right? So that's not changing at all. So am I going to take a derivative of that variable? Nope, it's not going to change. So I'm not going to take a derivative of that variable. So what can I replace it? I can replace it with the number, right? So that one's just 5. But now I no longer have L's. So it's only going to give me the dH dt. So instead of having a dL dt and a dH dt, I now only have one rate of change. So let's put this together. Volume equals, this is 5, that's 5, so 25 over 2h squared. Are we questioning there? Are we still okay? Okay, so let's take the derivative now. So I did all that work just to get to this point to set it up, and then take my derivative. I get my dv dt is equal to 25h dh dt. Now, units, this is important. My dV dt was 300 liters per minute. And the note that I gave you guys yesterday, it's 1. Wow, that's a horrible 1. Come on. 1. Oh, wow. Meter cube is equal to 1,000 liters. So what we need to do is we need to convert my liters into meters cubed. Now, I don't know if you guys probably haven't done these conversions since like 8th grade or 7th grade or anything, right? It's been a hot minute. Okay, so watch this. Liter over 1 minute. Okay, so if you guys haven't seen this before, this would be a good point to actually like try to pay attention to. We're converting. What are we getting rid of? We're getting rid of the liters, right? If we're getting rid of liters, to do my conversion, I'm going to put another fraction. Where does liters need to go? On the bottom. So liters goes on bottom. So I'm going to have 1,000 liters. And what goes on top in my conversion? 1 meter cubed. So in this process, my liters cancel out. And I end up with, so 1, 2, 1, 2. So that's going to be 0.3 meters cubed per, so I'm divided by 1 minute. Now, this process is super important because you're going to have to do this also by changing your time. Changing time is actually part of this also, because you can go from miles per hour to feet per second, where you have to do 2 different conversions on that. So now, by changing that, so that is now my dv dt all right, so now, because we're trying to get this item right here by itself. We're trying to get this by itself. I know what dv dt is, which I just got right there. So I got 0.3 equals 25. Now, what was my height? 1.5 times dH dt. And that's what I'm trying to get by itself, right? I'm trying to get that piece by itself. What's that going to be like? 25 plus 12.5, so it's going to be like 37 point 25? What? What is it? 25 times 37.5? Okay. All right, so 0.3 and then so do the math for me. It's going to be a small number.
Since that goes into a fraction and dH/dt is a fraction, do you not leave it as a fraction?
dH dt refers to something.
Yeah.
So what that implies, it's the change. So that is my delta. So the change in height divided by the change in time.
Okay, got it.
So think about it as like miles per hour.
Okay.
Yeah, so it's whatever the velocity is going to be. What did we get there? Huh? 0.008? Now, what are my units? Say it again? No. No. What is this though? It's just the height, right? If it's just the height that's changing, that's what they're asking for. They're not changing the volume, they're not changing the area, so it's just changing the height. And the height itself is measured in meters per minute. So now going back and talking about what this is, that means that as the water is going into the pool, starting at the bottom, and now we're here, when the height is 1.5 meters, okay, the rate at that current moment in time that it is going up is going to be this. So it's 0.008 meters per minute. So it's still increasing, but it's increasing a lot slower, right? So, make sense or is that nonsense? A bunch of nonsense? It's craziness, right? Now, do you guys understand the reason for doing the similarity now? Doing the similarity, because if I didn't, I would have a DLDT because my length is also changing at that time. So because the length is changing in that time, I have a change there and I have a change here. That's the reason why I had to set it up to do the proportions like I did all this. These problems right here are a pain. You will have several of them, but that's the reason why I'm trying to take like a whole day to explain this and make sure you guys understand. And then tomorrow we will be working with a little bit of more of this, but start tomorrow with some homework questions. So try, what's it, starting at 17 or 18? 19? Yeah, it starts at 19? Okay, so you guys, tonight, try to get from 19 through the next part. Do as many as you can. And if not, if you get stuck on it, then we'll go with those tomorrow at homework time. Okay? Alright, make sure you guys all like, share, and subscribe. Hit that notification button. Support my channel. Buy stuff for the merch store.